Welcome to our deep dive into Chapter 6, Work, Energy, and Power. In this video, we'll unravel the fundamental concepts that form the backbone of physics. Whether you're a student preparing for exams or just curious about how the universe operates, understanding work, energy, and power is essential. We'll start by defining these terms, explore their mathematical expressions, and see how they apply to real-world scenarios. By the end, you'll have a clear grasp of how energy moves and transforms, and why it's often called the currency of nature. Let's begin our journey into the world of physics. Physics, the term work has a specific meaning. Work is done when a force acts on an object and causes it to move in the direction of the force. Mathematically, work is the product of the force applied and the displacement of the object in the direction of the force. If there's no movement, or if the force is perpendicular to the direction of movement, no work is done. This concept is foundational, as it links force and motion, setting the stage for understanding energy transformations. Work can be positive or negative, depending on the direction of the force relative to the displacement. When the force and displacement are in the same direction, the work is positive. This means energy is being transferred to the object, like pushing a box forward. If the force acts opposite to the displacement, the work is negative, as in friction slowing down a moving object. Understanding this distinction helps explain how energy can be gained or lost in different situations. Kinetic energy is the energy an object possesses due to its motion. The faster an object moves, the more kinetic energy it has. This form of energy depends on both the mass of the object and its velocity. For example, a moving car or a rolling ball both have kinetic energy. This concept is crucial for understanding how moving objects interact and how energy is transferred during collisions or other dynamic events. Potential energy is stored energy based on an object's position or arrangement. The most common example is gravitational potential energy, like a ball held at a height. When released, this stored energy converts to kinetic energy as the ball falls. Potential energy can also be found in stretched springs or compressed objects. It's a key concept for understanding how energy can be stored and later released to do work. Work-energy theorem is a powerful principle in physics. It states that the work done by all forces acting on an object equals the change in its kinetic energy. This theorem connects the concepts of work and energy, showing how applying a force to move an object changes its energy. It's a bridge between the forces we apply and the motion we observe, making it a cornerstone of mechanics. Let's derive the work-energy theorem step by step. When a force acts on an object, it causes acceleration, changing the object's velocity. Using Newton's second law, we relate force to mass and acceleration. Integrating this relationship over the distance the object moves, we find that the work done equals the change in kinetic energy. This derivation not only proves the theorem, but also deepens our understanding of how forces cause energy changes in moving objects. Power measures how quickly work is done or energy is transferred. It's defined as the rate at which work is performed. In everyday life, we encounter power ratings in appliances, vehicles, and even our own bodies. The faster you do work, the more power you use. Power is measured in watts, and understanding it helps us compare the efficiency of different machines and processes. Mechanical energy is the sum of kinetic and potential energy in a system. It represents the total energy available for doing work. For example, a swinging pendulum has both kinetic energy, when moving, and potential energy, at its highest point. Mechanical energy is conserved in the absence of non-conservative forces like friction, making it a vital concept for analyzing motion and energy transformations. Law of conservation of energy states that energy cannot be created or destroyed, only transformed from one form to another. This fundamental law governs all physical processes, from simple machines to complex biological systems. Whether energy changes from potential to kinetic, or from chemical to thermal, the total energy remains constant. This principle is the foundation for understanding how the universe operates. Let's look at some real-life examples of the conservation of energy. When you swing on a playground swing, your potential energy at the highest point converts to kinetic energy as you move down, and back again as you rise. In a roller coaster, energy shifts between kinetic and potential as the cars move along the track. Even in a bouncing ball, energy is conserved, though some is lost to heat and sound due to friction and air resistance. Expression for kinetic energy is derived from the work done to accelerate an object from rest to a certain velocity. The formula is Ke equals 12 mv2, where m is mass and v is velocity. This equation shows that kinetic energy increases with the square of the velocity, making speed a crucial factor. The derivation involves integrating the force over the distance traveled, linking work and kinetic energy directly. Potential energy, especially gravitational potential energy, is given by the formula P equals mgh, where m is mass, g is acceleration due to gravity, and h is height above the ground. This formula is derived by considering the work needed to lift an object against gravity. It highlights how potential energy depends on position and can be converted to kinetic energy when the object falls. Elastic potential energy is stored in objects that can be stretched or compressed, like springs or rubber bands. When you stretch a spring, energy is stored, and when released, it returns to its original shape, releasing that energy. The formula for elastic potential energy is P equals 12kx2, where k is the spring constant and is the displacement. This concept is essential in understanding how mechanical systems store and release energy. Conservative force is one where the work done does not depend on the path taken, only on the initial and final positions. Gravity is a classic example. If you lift an object and then bring it back down, the total work done by gravity is zero. Conservative forces allow energy to be stored and fully recovered, making them central to the conservation of mechanical energy. Unconservative forces, like friction or air resistance, depend on the path taken and often convert mechanical energy into other forms, such as heat. When you slide a box across the floor, friction does work, and some energy is lost as heat. Unlike conservative forces, energy lost to non-conservative forces cannot be fully recovered, which is why mechanical energy is not always conserved in real-world situations. When a force changes as an object moves, we call it a variable force. Calculating work done by a variable force involves integrating the force over the path of motion. This is common in cases like stretching a spring, where the force increases with displacement. Understanding variable forces helps us analyze more complex systems where forces aren't constant. Collision occurs when two or more objects come into contact and exert forces on each other for a short period. Collisions are everywhere, from car accidents to billiard balls striking each other. During a collision, energy and momentum are transferred between the objects, and the type of collision determines how much energy is conserved. Elastic collisions are those where both kinetic energy and momentum are conserved. In contrast, inelastic collisions conserve momentum but not kinetic energy. Some energy is lost as heat or deformation. Bouncing balls are examples of elastic collisions, while car crashes are often inelastic. Understanding the difference helps us predict outcomes in various physical interactions. In a one-dimensional elastic collision, both momentum and kinetic energy are conserved. The final velocities of the objects can be calculated using specific formulas derived from these conservation laws. These equations help us predict how objects will move after colliding in a straight line, which is useful in many physics problems and real-world applications. Two-dimensional elastic collisions are more complex, as objects can move in different directions after impact. Conservation of momentum applies in both the x and y directions, and kinetic energy is also conserved. By breaking down the motion into components, we can use equations to solve for the final velocities and directions of the objects involved. Energy is often called the currency of nature because it's exchanged and transformed in every physical process. Just as money is used to buy goods and services, energy is required to make things happen, from moving objects to powering life itself. This analogy helps us appreciate why energy is so central to understanding the universe. Work isn't just a physics term, it's something we experience daily. From lifting groceries to climbing stairs, every action that involves moving something against a force is work. Recognizing these examples in our routine helps us connect physics concepts to real life, making them easier to understand and remember. Energy is constantly changing forms. For example, when you eat food, chemical energy is converted into kinetic energy as you move. In a light bulb, electrical energy turns into light and heat. Understanding these transformations helps us see the interconnectedness of different energy forms in our world. Not all energy transformations are efficient. Some energy is always lost, usually as heat. Power plants, engines, and even our bodies have limits to how efficiently they convert energy. Power measures how quickly this conversion happens, and efficiency tells us how much useful energy we get from the process. Energy sources can be renewable, like solar and wind, or non-renewable, like coal and oil. Renewable sources are replenished naturally and are more sustainable, while non-renewable sources can run out and often cause pollution. Understanding the difference is crucial for making informed choices about energy use and environmental impact. Machines help us do work more easily by providing mechanical advantage. Levers, pulleys, and gears allow us to apply less force over a greater distance. The total work done remains the same, but the way we apply force changes. This principle is used in countless tools and devices to make tasks more manageable. Friction is a force that opposes motion and causes energy loss, usually as heat. While friction is necessary for walking or driving, it also means that some mechanical energy is always lost in moving systems. Engineers work to minimize friction in machines to improve efficiency and reduce wear and tear. The food we eat contains chemical energy, which our bodies convert into kinetic energy for movement and thermal energy to maintain body temperature. This process is a perfect example of energy transformation in living systems, showing how the principles of physics apply to biology and daily life. Cars, trains, and airplanes all rely on energy transformations to move. Chemical energy in fuel is converted into kinetic energy, propelling vehicles forward. Engineers constantly seek ways to make transportation more energy efficient, reducing fuel consumption and environmental impact. Sports provide vivid examples of work, energy, and power in action. When a soccer player kicks a ball, they do work, transferring energy to the ball. The ball's motion is kinetic energy, and when it's caught or stopped, energy is transferred again. Understanding these concepts can even help athletes improve their performance. Nature is full of energy transformations. Waterfalls convert potential energy to kinetic as water falls. Plants capture solar energy and store it as chemical energy through photosynthesis. These natural processes demonstrate the universality of energy principles, connecting physics to the environment. Modern technology relies on our understanding of work, energy, and power. From smartphones to power plants, efficient energy use is a top priority. Innovations in batteries, renewable energy, and smart devices all stem from applying these fundamental physics concepts to solve real-world problems. Storing energy efficiently is a major challenge. Batteries, flywheels, and pumped hydro storage are all methods used to save energy for later use. The principles of potential and kinetic energy are at the heart of these technologies, ensuring energy is available when needed. How we use and generate energy has a huge impact on the environment. Burning fossil fuels releases greenhouse gases, while renewable energy sources like wind and solar are cleaner. Making smart choices about energy use helps protect our planet for future generations. Our bodies are remarkable energy converters. We transform chemical energy from food into movement, heat, and even thought. Every heartbeat, breath, and step involves energy transformations, making the study of work, energy, and power directly relevant to health and biology. Everyday appliances like refrigerators, washing machines, and lights use electrical energy to perform work. Understanding how much power each device uses can help us make smarter choices to save energy and reduce costs. Simple actions like turning off unused lights can make a big difference. Factories and industries consume large amounts of energy to produce goods. Efficient machines and processes help reduce energy waste and lower costs. Innovations in industrial energy use are crucial for economic growth and environmental sustainability. Communication technologies, from telephones to the internet, rely on energy to transmit signals. Electrical energy powers devices and networks, enabling instant connections across the globe. The efficiency of these systems depends on minimizing energy loss during transmission. Building structures requires significant energy, from manufacturing materials to operating machinery. Sustainable construction practices aim to reduce energy consumption and use renewable resources. Understanding work and energy helps engineers design safer, more efficient buildings. From concerts to movies, entertainment industries use energy in lighting, sound, and special effects. Efficient energy use ensures better experiences and lower costs. As technology advances, new ways to save energy in entertainment continue to emerge. Hospitals and clinics depend on reliable energy for lighting, equipment, and life-saving devices. Advances in medical technology have increased energy demand, making efficiency and backup power systems more important than ever for patient care. Scientific research, from particle accelerators to space exploration, requires vast amounts of energy. Efficient use and innovative storage solutions are key to advancing our understanding of the universe while managing resources responsibly. As our world evolves, the demand for energy continues to grow. Innovations in renewable energy, storage, and efficiency will shape our future. Understanding the principles of work, energy, and power empowers us to make informed decisions and build a sustainable world. We've covered the essential concepts of work, energy, and power, exploring their definitions, formulas, and real-world applications. From the work-energy theorem to the law of conservation of energy, these principles are at the heart of physics and everyday life. By understanding how energy is transferred, transformed, and conserved, we gain insight into everything from simple machines to the mysteries of the universe. Keep exploring and remember, energy is truly the currency of nature.